Okay, so welcome to the December Solar Chat. It's lovely to see everyone. And we've got Douglas, who's going to talk to us today, about the solar eclipse and things. So it's going to be a really exciting talk. So I'm looking forward to it. So I'll not waffle, I'll just hand straight over to Douglas and then we can have a good listen. So here you go.
Okay. Thanks, Alexandra. I started preparing some slides, and then the slides grew to about 40 in number. In fact, exactly 40 in number. So I'll try to whiz through those. A lot of them are just pictures of nice historical views of this experiment that I wanted to talk about, which is the attempts over the last century or so to look at the what's called the Einstein deflection of light as it passes close to the sun. Um, and let me try to pull up my slides and see if I can do a screen share. Uh-huh. Okay. Let's see. It's been a while since I did this.
Big green button in the middle.
And the green button. Okay, I'm pushing share. Okay, there we go. And I'll pick my there. Okay. Does that can you see something there?
We can see the
Okay,
whole.
all right. Then I will put it on the slide projector mode. Okay, how does that
Yep,
look?
that's brilliant. Perfect.
Okay, great. So I'll start reading through these, and the idea is that over the last couple of years, some amateur astronomers across the world have tried to reproduce the famous experiment first done in 1919 by Arthur Eddington and his team. Um, and why are they trying to do this? Well, first, I think people just like to be part of astronomical history and to repeat like difficult experiments that were done in the past and see if they can measure effects like general relativity with home equipment. And second, I think on a kind of maybe a scientific basis or is to show that actually modern amateur equipment using modern like triplet or quintuplet telescopes um, and digital cameras, very fast digital CMOS cameras, and computer software can allow amateurs to do extremely precise astrometric measurements. In fact, even better than what was done by people like Eddington and others in the early part of the 20th century. And in this regard, I kind of see it as slightly analogous to the topic of the spectroheliograph, in the sense that when the spectroheliograph was first developed at the end of the 19th century, beginning of the 20th century, the instrument was huge. It took up one or two rooms. And then over time, as the telescopes improved, the cameras improved, the software improved, it could be shrunk down to something that is very, very portable and that an amateur can use. And that's a an event that I think a lot of people on Solarchat can relate to. So as you go through this presentation, you'll sort of see how the scale of the equipment has shrunk over a century, and I think it's very analogous to the same technological trends you've seen in the spectroheliograph. So what are we talking about? In 1915, Einstein did a calculation where he integrated the path of a light beam from a distant star passing very close to the limb of the sun. And in his calculation, using general relativity, he would see an apparent deflection of 1.75 arc second at, at the limb of the sun. So at r equals 1 from the center of the sun. And that 1.75 number is worth remembering. It comes up all the time in these discussions. And so what that means is as you go further away from the sun, the deflection drops off hyperbolically. So as you get a few solar radiuses away, it becomes a fraction of an arc second. And so therefore you can start to see why it's a difficult problem. Um, Now, at the time, there was a Newtonian explanation for what the deflection should be, and it turns out it's half that of the general relativity calculation. And some people thought there should be no deflection at all, that it just didn't make sense that light would be deflected because light has no mass. So this, at the time, was an ongoing discussion. And primarily, it was actually a man named Frank Dyson, the astronomer royal at the time in Britain, who suggested that an expedition be mounted to actually resolve this issue. And his younger colleague, Arthur Eddington, who was at Cambridge University and was apparently a fantastic measurer, the two of them teamed up to propose that this expedition be funded. I think it cost a relatively large amount of money. I think it cost £1,000, as I recall, which was a lot of money in those days. Um, and they proposed to send an expedition to um, Africa and South America to make this measurement. And I found this cute YouTube video here, which I'll see if it works out, but it sort of shows some of the like dynamics involved. Let me see if this actually works, and you can hear the sound even. Could you all hear that? No, you couldn't hear it. Oh well, okay, that was difficult. But you could read the subtitles. It's kind of a cute little description of what was going on at the time. There's obviously some politics going on because this was around the time of the First World War, and as I understand it, the expedition, which was mounted after the First World War, was meant to be a kind of reconciliation between German and British scientists. Okay, let me go to the next slide. Okay, so uh, and the Dyson was able to get money and funding for. Hold on one second. Let me just. Okay, there we go. Um, for two groups to be sent, one to a place called Sobral in South America, and one to Principe, which is an island off the coast of Africa. Um, and this took two steamer ships to transport all the equipment. This is this setup in Sobral in Brazil, showing two of the instruments they brought from the UK. One was a 13-inch telescope, and one was a 4-inch telescope. The like big one is on the left in the circular tube, and the 4-inch is in the rectangular tube. Um, the 13-inch one used 16-inch glass plates, and the 4-inch one used 8 by 10 glass plates. So even the amount of photographic plates was a tremendous weight to transport. And you can see that they couldn't move the telescopes with a mount. They used the celiostat to direct the sun into the lenses. And actually, this was one of the major sources of error because the mirrors themselves tended to deform slightly when exposed to the sun. But the results were good, and I think in like retrospect was fairly conclusive. Particularly the 4-inch lens did much better than all of the other lenses they had. They had an 8-inch telescope as well in one of the locations, but the 4-inch telescope actually provided the best results. I think partly it was a result of having less seeing effects because of the smaller aperture. And second, it had a very, very long focal length. It had a 19-foot focal length, which meant that it was f57. So I think any aberrations that were there were like reduced by the long focal length. And until the mid 20th century, it was believed you needed at least a focal length of f40. So the results were announced in November of 1919. And what this graph is showing is the dotted line is what would be expected if Newton were correct. And the black solid line was the line expected if Einstein was correct. And the sort of light line is the best fit to the data. So you can also see here, this is plotting like distance in a kind of inverse distance, right? The close distance is actually to the right, and the far distance is to the left. And the displacement you see is in arc seconds vertically. So you can see very close to the sun, you actually get better measurements because the displacements are bigger. And that's a typical thing you see. You're better off if you have more data close to the sun than far away from the sun. But this, I think, pretty well proved that Einstein was correct versus Newton, but people wanted to really know how accurate Einstein's calculation was. So they kept on repeating the experiment. So there were a number of attempts between 1919 and 1973 to verify it again. Can you still hear me, by the way? Are you still able to hear me?
Yep.
Yes.
Okay, that's perfect. And I'll go over these because, as I said, people like to feel part of history when they do this experiment. They want to feel like they've gone back to these explorers who were tramping their way through Australia and Sumatra and in Egypt, with their giant telescopes and so on. So they want to feel part of the adventure. So I'll just go over the two expeditions which have some interesting photographic history behind them. That's the 1922 Australian expedition and the 1929 Sumatra expedition. So this is the results from one of the 1922 telescopes that was done by the Lick Observatory in the US. And here the data is plotted actually a little bit differently. So its distance to the sun it increases as r, going to the right. So that's in solar radius. And then the deflection in arc seconds. And this is actually like pretty good data. There's not very much scatter, particularly close. And what you see is that their eclipse field was very, very symmetrical, which has some advantages to it. That's the little circle on the top right. And they did a least squares fit. And as you can see, the least squares fit hits r equals 1 at around 1.75, which is the expected result from the Einstein calculation. And as you can see, the further away from the sun you are, the noisier the data is because the deflections are quite small. And here they had a very, very large plate. I'm assuming they also used about 8 by 10 size plates. And they went out to r equals 12, which is very, very big, actually. And so this is the size of their equipment for the Lick expedition in like 1922. They had to also send a couple of boats. I think they had teams of donkeys and huge number of workmen as well to like set up the telescopes. This is one of the telescopes being set up, and I quite like the caption of this. It says, the caption says, Miss Elizabeth Campbell at the Floyd Telescope, which I thought sounded very like early 20th century somehow. And the captions for these photographs, on the left, it says, Dr. Tumpler observing the sun through Lick Observatory's 5-foot camera. So obviously a big camera. And on the right, one of the large cameras used to capture images of the sun of the eclipse in 1922. So again, you can see the scale of the effort that was required in those days to do this experiment. And you even needed, apparently, I think, mosquito netting, it looks like. Okay, the 1929 expedition, which was done by a German team to Sumatra, um, also gave some good results. You can see here that the least squares fit again intersects at r equals 1 at about 1.7. So I'm in agreement with Einstein. They used a couple of interesting new approaches to try to get like better calibration, which I'll show you in the next slides. One problem was that their star field wasn't very symmetric, as you can see in that circle in the top right. If you have a very symmetric star field, some of the errors will cancel out. And so this is one of their novel telescopes. The caption here says, Professor Erwin Finley Freundlich led a scientific group from Germany consisting of 6 astrophysicists from Potsdam. Freundlich and colleagues designed the most precise camera to capture pictures of stars around the sun. They brought 15,000 kilograms of instruments to Belawan to be set up in Takengon. So what you can see here is they used a double camera. You can see there's 2 photographic screens visible in this picture. And as I understand the concept here, they wanted to simultaneously capture a field away from the eclipse where there was no gravitational distortion in order to solve what's known as the plate scale problem. That is, what is the actual plate scale calibration you're using at the time when you're making the measurements, because that can lead to all sorts of complications and errors. So I think what this setup is doing is that there's some mirrors and half-coated mirrors and so on in order to take pictures of the eclipse and of a field somewhat away from the eclipse field. And this is another telescope which they brought to the 1929 eclipse. And the caption here says, Erwin Freundlich on the 1929 expedition to Sumatra, this triplet telescope could be moved away from the sun during the eclipse to capture a reference image, but mechanical deformations appeared to cause problems with this approach. With large, heavy telescopes and cameras, any significant physical movement was both difficult and could cause optical distortions in the observing system. So the idea here is that they used advanced triplet, which I guess at the time was quite new. I think it was made by Zeiss. And so it led to a relatively compact telescope. And they brought a normal kind of mount with them so they could slew the telescope and thereby take one plate image of the eclipse and slew to one direction and take an image of the stars in a calibration field. But it turned out the simple movement back and forth by, let's say, 10 or 15 degrees caused some bending of all the structures involved, either the camera mount, because the plates are very heavy, or the telescope itself, because the lens was very heavy. So that approach was thought actually, although theoretically a good way to do it, not very practical. And I think that was abandoned in later attempts. So there was a pause in how of doing this experiment until 2017, when Don Bruns decided to revive it using more modern equipment. Here he is with his TeleVue 101. And you can see over time, everything got smaller. The telescope got smaller, the camera is smaller. He used a CCD camera from Finger Lakes. The mount is correspondingly smaller too. And he went to a very good location in Casper Mountain, Wyoming, which was very high up, like 8,000 feet. And it was very, very cool up there, about 10 degrees centigrade. So the seeing was excellent and he had no clouds and he got extremely good results. As you can see here, the scatter is very small and the result he got was extremely accurate. I'll just mention here, this is a summary of the equipment that he used. Um, uh, he used a very good telescope with a very flat field, which helps because if you start off with a field that's less distorted, then you don't have to worry as much about correcting for distortions. He used what was for the time a good camera, but for these days very, very slow. And in fact, his um, um, experiment was kind of data speed limited. He could only take about one frame every 1.5 seconds. So that meant he didn't have very much data to work with. Um, he also used some commercial software packages to analyze it. He used the Maxim DL and Astrometrica, and then he used some code written by him and some relatives and friends, and it was written in Fortran and Visual Basic and MathCAD and Excel to do the analysis, which took, I think, between 3 and 6 months to do the analysis, even though he only had about, I think, 50 like data pictures to analyze. And what he was able to do, I think for the first time, was he took two calibration fields, one on the right and one on the left. This is what I had mentioned had been tried many times before, but unsuccessfully. So what he'd first do is he'd start off on the right and take a calibration field away from the sun, where, okay, can you still hear me?
Yes, we
Hello?
can
Can you,
hear you. Yeah.
okay. I just had a message come up on my computer that there was an audio problem. So he would take a field about, I think it's about 12 degrees to the right, um, and then, but that would be when totality had already started, so the sky was pretty dark, and then slew to the sun and take the eclipse field, and then towards the end of the eclipse, when there was still totality, he'd slew to the left, again about 12, 13 degrees. And at that point as well, take a calibration field. Now, the advantage of doing right and left is, in terms of solving what's called the plate scale problem, is that one of the like issues with is with the telescopes is thermal expansion of the tube, which changes the focal length, which then changes the plate scale. So I think the idea is if you take a field before the eclipse and after the eclipse, and there's some, let's say, linear change in the temperature, if you average the left and right calibration fields, it should like give you a good result for what was taken in the middle, which is the eclipse field. So anyway, that's the theory, and it seems to have worked out really well. He got a very close result to what was expected, probably the most accurate result ever using this method. And I'll mention here, this is a simulation I did uh, using Stellarium for what the eclipse field looked like on that day. And you can see there's two bright spots. Let me see if I can just see. There's, two bright stars. This one here and this one here. And those are of magnitude 7.1 and 7.5. And along with this star, they're the three brightest stars in the whole field. And they're also quite close. One is at 1.5 radius from the center, and one is at 1.6. And it turns out those are extremely rare that it would happen. You'd get two symmetrical bright stars like this quite close, and they were really close to the corona. I think Stellarium does a pretty good job at like imitating what an eclipse corona looks like, but that's pretty much how it looks in the data images I've seen actually. So you have to be very careful of not saturating when you take pictures where the stars are very close to the corona. But those allowed a very accurate result. I'll just back up here. You see, these are the two close stars, which are at around 1.5. And also the fact that they're symmetrical around the sun means that any systematic error gets canceled out to some degree. So I think that also helps explain why the result was so good. Okay, let's jump ahead to 2024. And by that time, a lot of other people became inspired by Don's 2017 result. I think he won an astronomy award for the experiment, and two groups of amateurs organized themselves to be in what we thought was the highest probability areas of success. Um, One in El Salto, Mexico, which is somewhere up here near Durango, which is supposed to have the best theoretical cloud conditions, and another in Leakey, Texas, which is right here near the border of Mexico. Um, it turns out that, in fact, statistics only get you so far, and on the day, there were quite a few clouds. In fact, some of the best uh, conditions are up here in like Vermont and Quebec, way up here, uh, which had probably the lowest probability of being cloud free. But in fact, this is a picture taken by a Solarchat member in Sherbrooke, Quebec. Beautifully clear skies. Would have been great to be there. Instead, I'll just show you some images from the team in El Salto. So this is on the day of the eclipse. You can see all five stations. They used like televiews, 101, the same as Dawn used, and a variety of cameras. This is actually a very professional looking picture because it was taken by a science reporter from the Washington Post who decided to spend like a whole week with the guys down there and write a like a long story about it. So like that explains why the picture is so dramatic. This is one of the guys, Daniel, with his Teleview NP101, and in this case, he's using a ZWO 1600 camera, and you can already see the problem in the background. There's some clouds, and there's also wind, Um and the clouds weren't this bad during the eclipse. But I think what happened is that before the eclipse, you have to do a focus on a like, reference star, on a bright reference star. And I think what happened is that it was cloudy enough that the focusing was very, very difficult. And if the focusing is not very good, then you don't have uh, sharp star images. Okay, these are some pictures of like Leakey, Texas on the left. This is Don Bruns, who did the 2017 experiment, and he brought along the same telescope, the Teleview NP101, but he used a different camera. He used the ZWO 2600. And like, this is my friend John, who I went to university with, and this is my like telescope that I brought, which was an ASCAR 65 PHQ, and I used a ZWO 294 camera and then a very small mount. And actually, I could put all my telescope into airplane luggage because I didn't want to ship it. So I made sure I could break it all down into like a suitcase that would fit onto an airplane, you know, the 23 kilogram kind of weight limit. This is a professor named Kenneth Carroll who organized a large group of students to participate in the experiment, and he used three telescopes. He used an NP101 with a ZWO 2600 and an ASCAR FRA 500 with a 1600 mm and a Sharp Star 94 with a ZWO 183. And it turns out all those different telescopes we used were able to help us determine what might be the best equipment for the future. And I'll go into that in a minute. And so this is one of Kenneth Carroll's students, or like two of his students, working on the NP101 with this like 6200. And this is a team working with the FRA 500 and the like 1600 camera. So here's a summary, by the way, of some of the equipment that was used. You know, the telescopes had different focal lengths and apertures, but all were kind of in this area of around 4 inches, shall we say, 3.5 or 3 to 4 inches, which I think not coincidentally is the same size as what gave the very good results from Eddington. the 4-inch, like 19-foot focal length telescope. I think that sort of range, 3.5, 4 inches, is what tends to give you like good results in this sort of experiment. I think um, primarily due to seeing effects. And you can see here the image scale is around, let's say, 1.8 in like a lot of cases. And I actually used a very small like image scale, 1.14. Um, and so, as I said, if you do the calculation of what the deflection is going to be, at let's say 5 solar radius, the expected displacement is 1.75 arc seconds divided by 5. And that corresponds to about 0.2 pixels. So you need to analyze the data to sub-pixel accuracy, which is the challenging part of the analysis. And that was true in 1919, and it's true in 2024 and 2027. You need to be quite good at finding the centroids of stars. And maybe this is a good point to mention what are the errors involved. I think fundamentally, the precision of the star locations is seeing limited. So the better your seeing conditions are, like high altitude, probably low temperature, then you'll get better centroiding. That's as long as you can adequately compensate for optical distortions of the telescope and other parts of the optical system, and as well as some other things like refraction errors, which should be able to be done pretty accurately, although it's a bit time consuming. So this is what the eclipse day looked like in Leakey, Texas. This is a picture I took with a like ASCAR 180 on like just a normal like DLSR. So it was cloudy, and so the people in Leakey, Texas weren't able to get any good data. The people in El Salto in Mexico got some data, but clouds and wind and some other issues caused some problems. But we were able to do some analysis. As I mentioned, the large number of different equipment led us to reanalyze the data of what the best equipment probably is for this experiment. And it seems like the ASCAR FRA 500, which is the 3.5 inch f5.6, combined with ZWO 2600 camera, that seems to be the best combination. The mount is probably not so important. I know people are using ZWO mounts, and some are using Celestron mounts and things like that. I think the mount isn't particularly important because you don't need great tracking, for example. Probably what's more important is just portability. So you can see here how everything has shrunk over the years, like from a century ago. You're using not that different an aperture than the Sobral experiment in Brazil of Eddington, but the focal length has shrunk from 19 feet to 500 millimeters. And the camera has shrunk from 8.5 inches of glass to a fairly small CMOS. So in the remaining time that I have, I'll go over a bit about the software analysis. Because as I said, when in the old days, when you're using glass plates, you had some sort of mechanical contraption with micrometers and so on, and you'd have people trying to find the center of the stars, and it took, I think, months and months to analyze the selection of plates. And when Don did it in 2017, when Don Bruns did it in 2017, he had a whole bunch of various software programs that he had to sort of cobble together using various scripts and so on. So my son and I decided to create an integrated package that we call the MEE 2024 Stacker. And it actually those who may know, it sort of looks a lot like our spectroheliograph software because we reuse the same interface, the user interface, as for that. And we just kept on adding features and features and features to it as some of the team requested them. So it ended up that this is the one program you need to do everything. It stacks, it finds the centroids, it does a plate solve, it computes optical distortions, it calculates the refractive distortions, it does a least squares fit, and it provides some graphical output. So I won't go into all the features here, but this is what is called tab 1 that is sort of like the input page where you enter in all your frames that you want to stack and so on, and it does a preliminary plate solve for you. And like this is what we call tab 2, which is actually the part of the program that does most of the analysis. So for example, you like set your like observing time. It knows what the plate solve was. It matches the apparent star locations with a Gaia catalog that's available like online. You can enter in where you were in the world. It computes the refractive errors, depending on how high above the horizon you're taking the images. And it does some complex optical distortions, compensation for the telescope you're using. Most telescopes have what's called a cubic distortion, although some have more complex, like quintic distortions, as we found out. And then in the final tab, this is what we call the analysis tab. You can like take all your data, and it will figure out the least squares fit to find out this like Einstein coefficient, so-called. This is the 1.75 arc second number. So we built this program, and we ran the like data through like Don Bruns's 2017 data to see if it worked, and it agreed very much with what he did. So what this screen is showing is it shows the 17 stars or so that's apparent in the 2017 data. These are the two close stars here, this one and this one. They're like flipped left and right because of the RA is flipped in a sense. And then this is the other bright star over here, I think 7.3 magnitude. You can see in very, very fine font, you can't quite see it. This has these points have a Gaia catalog number and a magnitude. So this is 7.3, this is 7.5, this is 7.1. And this black dot is actually not the sun, this is actually the moon. So then what the program does is it does least squares fit. This is a least squares fit. So you can see this curve, and the minimum is where the least squares is minimum, and where the error is a minimum. And you get a deflection constant of 1.74, which is about 0.4% off from the Einstein number. We get a kind of an error estimate of 2.1%, which is based on the residual like RMS on the error divided by the square root of a number of stars. It also agrees pretty well with like Don's error estimate, which was on the order of about 3%, I think, was like his estimate. So we were pretty confident that the software worked. And so also this is Don's like data plotted where the solar radius is on the x-axis going out from 1 to about 5. So a fairly small field, actually. You saw some of the earlier expeditions had fields of about 11 or 12, but he had a quite small camera. And these are the two close stars, which as you can see are on like opposite sides. So whatever errors like compensated nicely. And you can see the scatter is very, very nice too. So in 2024, turned out there were a few problems. One is that the distortions for some of the data were much more complex than we expected. Like I won't go into all the reasons for that, but our software was able to figure out what this complex optical distortion was. It's small. It's on the order of a couple of pixels at the edge. And like this is a very, very large frame. This is with a 6200 camera. So it's quite a large frame. But as I said, you have to know the errors to within a fraction of a pixel. So if your errors are several pixels, you won't be able to get a good answer. But the calibration fields, which are done on like nighttime star fields, can provide excellent correction. So one of the fields in Mexico, which had some pretty good data, as I said, was using a very large field camera, and was able to get over 170 stars, down to magnitude 12 or so, which is a very large number of stars. Most of the previous expeditions only had maybe a few dozen stars that were visible. So we had a very large number of stars, which is good. And it turned out that this particular setup was not able to do a calibration away from the sun. So it was not able to actually do the whole calibration process to eliminate the plate scale problem, which Dawn was able to do in 2017. So this actually was a bit of a reproduction of how the original Eddington experiment was done in the early 20th century before they were able to slew the cameras. But nevertheless, it came up with the result. There's a lot of scatter and noise, I think, due to some of the environmental issues. But the result came to within 5% of the accepted value, which isn't bad. And it showed that I think the technical challenges can be resolved. We know exactly what went wrong, but most of those are things that are a bit beyond what a person can deal with. It's weather-related issues, like always, and you only have one shot at doing it. And if your environment isn't very cooperative, then things won't go right. So so that is the end of my presentation. So I'll reduce this and I will stop sharing. And if there are questions, I went over a lot of material pretty fast. But if someone wants to dig in more deeply to any of those things that I brought up, please fire away.
Fascinating, Doug. That was interesting. Thank you.
Thanks.
Thanks.
Yeah, really good. Quick question, Douglas. How much do the stars wobble around? I don't do nighttime astronomy, so I'm just thinking, you've got the sun there. The seeing conditions won't be ideal. So how much wobble, for want of a better phrase, is there on these stars that you're trying to use as reference points?
Okay. Well, I'll just mention that actually an eclipse is basically a daytime solar observation, right? So, and I think it's that wobble, as you call it, during the daytime observation, which is really the limit. So let's say, I'm guessing, let's say on some average, you might get 3 arc seconds, right? Something like that. Now, I mentioned that there are some nighttime calibrations you can do. And so the nighttime calibrations, you can get much better results. And that's what we use for calibrating the telescope. So what you generally do is, let's say the night before or the night after the eclipse, you would take some calibration fields. Generally, they're called zenith images, meaning you point the telescope straight up to a dense star field. It doesn't have to be exactly vertical, and you take a number of nighttime images and stack them. And usually you can do pretty long exposures in order to get a very deep field. So maybe you'll take a field of a couple of thousand stars at, let's say, 1 or 2 second exposure. And those ones, I like did some in Texas because the day before the eclipse, the viewing was really good, and I think it was probably maybe 1.5 arc second seeing or something. It was really really good. At nighttime, it was quite cold, but I think, and so you get very good calibration from the nighttime, but the daytime it's just like solar astronomy. You'll have probably around 3 seconds, 3 arc seconds. And so you're, as I said, trying to find the centroids of stars to within, let's say, zero point 0.1 arc second, but the centroids themselves are maybe 3 arc seconds.
Yeah, exactly.
So that's the challenge.
Yeah. So is that easier to do with the old photographic plates or digitally?
Oh, I think it's much easier digitally. Yeah, much easier digitally. I'm amazed they could do it with the old photographic plates because like digitally you can see like a true centroid, right? Like you can like let's say that the stars are, let's say, 3 arc second, and your pixel size is about 1.5 arc second. So a star will span a couple of pixels, and so you could really see the shape of it, and then you can use some algorithms to find the center of the centroid. I don't exactly know how they did that photographically. I think that was an art. I did read recently that someone in the last 10 years or so went back and reanalyzed the Eddington plates from 1919 with, I assume, some digital technology, and he found the results essentially the same. So they seem to know what they were doing back then.
Thank you.
Doug, great talk. Thanks very much. It's something I've been interested in quite a while as a bit of an eclipse chaser. And I seem to remember in 2017 and seeing Regulus over to the left-hand side of the sun, and it coming through in the images in my DSLR. And often thinking about, wouldn't it be cool to repeat the Einstein experiment? It did strike me all right, trying to pan across maybe 15, 20 degrees each side. Like an eclipse is a very short event. It must have been quite a race against time. I mean, like a 2 minute eclipse feels more like 20 seconds. So to pan across, take some exposures, pan across the other side, I mean, that's it's quite a race. I think it makes a lot more sense, perhaps, as you said, to the calibration images at nighttime.
Oh no, you must do the calibration. You must do some calibration images at like nighttime, but those are primarily looking at the higher order distortions of the telescope. As I said, this sort of complex optical curvatures, which are generally called cubic and quintic distortions, and those apparently do not change with temperature. The thing is, though, that with temperature, the focal length changes to some degree, right? And so therefore what's called the plate scale, which is the linear distortion, changes. And that's the one where you need a calibration very close to the eclipse, or during the eclipse, I should say, right? So, and so that's the idea of slewing, let's say 10 or 15 degrees right or left.
So you're
You need
slewing
both.
because the air temperature will typically be higher during the daytime. That will tweak obviously your tube will expand, would increase your focal length, which would change your image scale. And you need that to calibrate that in order to the relative, it's more a linear relationship across the whole field as opposed to the distortion elements.
Exactly, because what the problem is mathematically, a linear distortion looks not that different than a 1/r distortion, as it turns out. So you can confuse the 1/r with the linear distortion, and trying to disentangle those two is a problem. And that's kind of the history of the whole experiment, is trying to figure out this plate scale problem, which is why for many years people tried to take this calibration field away from the sun. But you can imagine, moving a telescope with with a 50-pound camera or whatever is going to be challenging. These days, it's not such a challenge. But as you pointed out, you don't have much time to work with things, so you do have to have an automated script of some sort. So in 2017, Don was using the sky to automate his mount, and I think a lot of people use the sky as well in 2024 to take calibration fields and eclipse fields. I'm proposing to try to use SharpCap in 2026 to use a kind of a version of what people use for spectrophotographs, right? To control the camera and the mount. Because some people in 2024 were using, let's say, like ASI cap to control their camera and the sky to control their mount. And sometimes there was a problem of having the timing coordinated exactly. So I propose, maybe try to use like SharpCap to control both the camera and the mount.
Yeah. Or you could try Nina, for example. That'd be another option as well.
Maybe Nina too. That's another good.
Yeah.
Yeah.
And did you look into it all in terms of things like I know the Canon lenses certainly have it. I'm not sure on the Nikon where their field curvature and distortion is already mapped and stored in the likes of Photoshop, where you can actually read the lens from what the data that's embedded in the file, and then be able to correct, on a typical image. Was that looked into at any stage to try and rather than trying to do it,
Well, it's
from scratch,
actually,
actually?
I see where you're coming from, but it turns out the nighttime calibrations are pretty easy to do. So you may as well just test your lens because the average, whatever the manufacturer might provide, is probably not going to be exact enough for what your lens is. And the easy part is the nighttime calibrations. In fact, I'd say one of the problems was a lot of people didn't do enough testing. Like you need to start preparing, I don't know, a year before, like testing your equipment, testing the mount, testing your control software, practicing focusing. Like one of the hard things I mentioned was try to focus basically in a condition which is more like dusk. During eclipse, the stars away from the sun are kind of like dusk-like conditions. Try to focus on a star at dusk. It's not easy, but if you're out of focus, then you won't get good centroids, obviously. But I should mention that in theory, right, like these ASCAR telescopes, they're kind of like sophisticated camera lenses, right? In fact, ASCAR makes kind of camera lenses as well, short ones. And lenses like the Samyang, do I have it right?
Yeah.
Those lenses are good, like astronomy lenses. I think in principle, you could do this experiment with a very good DLSR prime lens of some sort. And I think you could probably even use like a Canon DLSR. There might be a little bit of a problem, if you have an RGB kind of Bayer matrix, your effective pixel size is rather big. So I'm not quite sure if that will really work out. I have a feeling the pixel size might be a bit too big. Like effective pixel size is a bit too big. So you probably may as well, just use a monochrome camera, which are not that cost different than a good Canon camera. But as I said, these like ASCAR lenses, which seem to have been produced to give extremely flat fields these days, are kind of basically fancy camera lenses, right?
Okay, thank you.
Douglas, where are you going in 2026 then, and how many are going to come?
Well, 2026 is not a great eclipse for a few reasons. I guess the best place to go is Spain. I actually have a friend who lives near Santiago de Compostela, which isn't too far away from where the eclipse path is. The eclipse is quite short, and it's also fairly low to the horizon, which causes some issues. Um, but I know a few people who are going to go there just to do a sort of dry run, in a sense, because what they're really trying for is trying to do this again in 2027 in some exotic place like Egypt or Tunisia or someplace like that. And as I said, a lot of this is a kind of educational experience. It seems to be a lot of science teachers, sort of high school, college teachers, are getting students involved. And so even if 2026 isn't a great eclipse for this sort of thing, I think it's a bit the experience itself, and feeling you're doing something really hard. And also, I think there's a like a collaborative aspect. Like, for example, the team spirit in the place that I went to in Texas was like fantastic. You know, it was really really fun, and I'm sure the same was true in the place in Mexico. Apparently, they were staying at some like motorcycle club hotel or something in the mountains of Mexico. Apparently, it was really wild. Um, but everyone seemed to have a great time, like setting up equipment, taking the data, and also like analyzing it as a team. So and I didn't show you, but there was a pretty lengthy paper that was produced in a astronomical society that came out, and so people I think had fun. Students and some professors had a lot of fun putting the paper together as well. I should speak to
To
maybe,
2027.
excuse me.
Are you going to go to the 2027 one
I
then?
don't know. They're all in such hot, dangerous places, you know. Maybe I can ask the people here where they think the best place to go. I think Christian said he's thinking of Tunisia, right? And I'm like not sure about the other people here. Maybe they can provide some insights of where a good place to go is.
I would suggest south of Spain.
Yeah, that's where I'm going to go.
Yeah,
I'd say Gibraltar is what I was looking at when you were talking. So, yeah,
yeah. Just a word to note that there are a few in North African countries like Algeria and adjacent countries where um, telescopes and even binoculars are not allowed in. They will be confiscated at customs, and you'll get them on the way home.
Really?
Okay, it's done for security reasons. So that's a topic that came up on a conference I was actually earlier in the year. So from people who have gone
interesting.
there. So I'm not sure if it applies to Tunisia, but it certainly applies to Algeria. And I think there's three countries in total, just each other.
Strange.
Hmm.
One thing I learned from this experience in 2024 is how much better weather forecasting has become, actually, right? In the US, I don't know, the National Weather Service was 7 days out able to provide extremely accurate modeling of what the weather was going to be, let's say in Texas and Mexico. And we already knew, like a week out, that we'd be in trouble in those locations. Like to the hour almost. I was really impressed. The computers and the data taking have gotten so much better. And I think the real eclipse chasers, they don't decide until the last minute where they're going to go. Like, in fact, when I arrived in Texas, there were a whole bunch of people there, and they said, we're packing up and going to Oklahoma uh, because it's not going to be good here. And they knew that, I don't know, three, 3 days or so before. And even before I flew over there from England, I could tell, okay, this isn't going well in terms of weather. But you know, you make all these plans with other people and hotel reservations, and so and you're sort of trapped in a sense, right? Um, um, so if you really want a good result, and you're a team, I think one of the faults is everyone was clustered in two locations, right? Would have been better if people had been spread out along the eclipse path and then higher chance of something good happening.
We
Yeah.
need to invest in the Solarchat tour bus. Yeah,
That's the next fundraiser.
exactly, yeah.
Yeah, to your point about the weather and pivoting, we were in New Orleans like the day before the eclipse, purposely staying over, and we had to make a last minute decision to head north. We were heading to Texas, but we headed north to Arkansas to get clear skies. So yeah, you have to be ready to pivot last minute.
Hmm.
Mm.
Yeah, my brother who lives in Ohio, same as me, about 2 hours from me, he went to Texas. I stayed home. It was gorgeous at his house in Ohio, and he had clouds in Texas where he was at. It was like, oh well.
Also, another
Cool.
thing, Douglas, what I noticed is in one of your slides, I think that it was the guy with the t-shirt that said like a dark
Hello,
star or something,
darkness,
my
my old
old
friend.
friend.
Okay.
Yeah,
There's a big plate next to him. And I was wondering what that big plate was.
a big plate. Let me.
Yeah.
Oh, the round one?
Yes. Because it looks very similar to something we saw on Orkney, which was it's like got little holes in it, and they use it for orientating where the stars are on this one
Oh,
particular professional instrument, which I can't remember what it's called.
oh, okay. Well, let me have a look at that. Here. Let me see if I can go back to sharing that one. Right?
It hasn't come through yet. Just hang
Not
on a
up
minute.
yet.
That's
Yeah.
it. At the bottom, there's a big metal plate, and I
Um,
was wondering what that is.
Hmm. I'm not sure what that is. I never really noticed it before.
Yeah, so it does, because it's like 1443. It does look very much like that plate from that professional telescope where they put little holes in. But I could be wrong. I don't know.
just something
Uh,
to sit on.
I don't know. That's quite a funny thing.
Mm.
I'm not sure what that's for.
It,
Huh.
So he wasn't at your site, he was at the other
No,
site.
he was at my site. Yeah.
Oh, right, okay.
Yeah, yeah.
But you didn't notice it.
Was so busy, I just went around quickly
Yes.
and took photos, and I didn't really inquire, like, what's that big piece of metal you have there? But he was sort of a little bit local, so he could throw all this equipment into a truck because he came from a college not far away from here, and so I don't know what
Mhm.
that could have been.
Oh, well, fascinating.
Maybe it's symbolic of some sort. Uh,
It's amazing what you notice.
Very
yeah,
very
I can
good.
ask him actually. I can send him an email and say, "What is that thing? I just noticed."
Well, yeah,
Um,
I'll be going in 2027. I'll be going to the south of Spain. But I don't think that I'd be able to do that sort of calculate. I don't have the setup for that, but I think I'll just go and watch the eclipse if
yeah,
it's not cloudy.
it's well, in fact, most of the people like Don Bruns, he said, I want everything to be automated. I don't want
Mm.
the experiment to destroy my eclipse experience. He said,
Mm.
I'm here with my wife. He always brings his wife when he travels, and he says, no, everything is fully automated. The system makes a few beeps and so on, and then I'm just there enjoying it without any cameras. I'm just, enjoying the moment with my family. And then at the end, there's a couple of beeps, and then I'll spend my time analyzing the data later. But everything should go smoothly without any interruption of my
Mm.
emotional experience.
So how long is the 2027 eclipse?
Very long.
Oh, really?
Yeah,
Like 12
very long.
minutes?
in
Like
I
Egypt,
think
it's
it's
7 minutes, isn't it?
yeah,
Wow.
it's
7?
Yeah.
yeah,
In
Wow.
yeah, it's
Egypt, I believe it is.
yeah. In let's say Gibraltar, it's like four, but four is
Yeah.
already pretty long.
Yeah.
The 2024 eclipse at the maximum was, I believe, 4 minutes.
Two. Yeah.
And in 2017, it was only 2,
2 minutes. Yeah.
um, which is why in 2017, Don was very, very data limited because his camera would only take, let's say, 1 frame every 1.5 seconds. I think he collected around 50. Um, uh, and he divided between eclipse images and and the calibration images. So he did not have very much time to take images on the sun. 2024 was a much longer eclipse, and also the cameras were faster. 2027 is enormously long if you're near the maximum. But I'm not quite sure whether being in the middle of a desert where it's really hot is such a good idea, because then I think the seeing might get worse, right?
Yeah.
And
Mm.
all the heat rising from the ground, and it's going to be around noon or so too. So
Yeah.
it's going to be really hot. So I thought actually you might be better off in a coastal location if you wanted to do this sort of experiment at least, like either on the Red Sea or the Mediterranean. Um, but then Christian claims that then there'll be too many clouds if you're in a coastal area, so you're better off in the desert.
Don't
So
say that. I'm going to the coast.
yeah, it probably depends what you want to do. Because as I said, I think the reason why Don did very well in 2017 was he was on top of a very cold mountain, um, and so I think the seeing was really really good. I mean, I've seen his data. I've analyzed the data myself, and I could see the seeing was really really good. And he also got really good focusing. Like I think again, it's one of those skill things. And when students, you can automate a lot of the stuff, right? Like you can automate a lot of the mount motion and the camera, but focusing, as we all know, is something generally you do, with touch, right? And if you get panicky, and also if you start second guessing yourself, I realized like some people said, "Oh, I got focus, and then I'm going to go back and try to fix it because I can make it better, and I'm going to use a Batnikoff mask, and I'm going to do this, I'm going to do that," and then they get all panicked, and then it turns out that they're out of focus. Um, so I think, and as I said, although you could probably on a nighttime star field do some automated focusing, like with an electronic focuser and something, I think that's really hard to do on like a daytime star field. It's really kind of an art.
Like I would be concerned about the heat in, well, two issues. If you go to the likes of Egypt, it's going to be quite expensive and quite limited in terms of accommodation and flights. And you could potentially be at the high 40 degrees, maybe even 50 degrees Celsius, with
Hmm.
extreme heat. And
Mm.
the mind and the body doesn't necessarily work very, very well when you're trying to race to observe an eclipse. And then you have the equipment, even things like the cooler on the camera, for example, trying to make sure that doesn't have problems. The computer, trying to keep that cool. Will that work at the time you need it? I will be a bit concerned. Whereas I'm just looking here, south of Spain, and not just Gibraltar, but there's quite a region around it that is several airports. It's all about the 4 minute mark. So there's lots of options there, I think.
Right. And as I said, I think things like weather, you can't, I mean, my experience was in 2024, you can't use statistical uh, data necessarily. I mean, the worst place to go would have been like upstate New York or Canada from a statistical perspective. But on that day, it was the best place to go.
Has anybody got any other further questions? Or should we bring this to a close? And also, I want to say a very warm welcome to Carlo. Although I think Carlo got the time wrong and he joined an hour late, but never mind. It's still lovely to see you. Hello and welcome. But if anybody has got any other further questions, or should we close? Um, I
Good to
think
see everybody.
yes, it
Yeah,
is.
likewise.
Thank you,
And
Dan.
thank you, Douglas, for doing
Yes.
such a
Excellent.
great talk. It
Yeah.
was really
Thank
interesting.
you.
Really enjoyed
Interesting.
it.
That's great. Thanks.
Thanks a lot.
Thank you, everybody.
Okay,
Cheers,
so
everyone.
close up now.
Yeah.
See you.
Take
Thanks,
care.
folks.
Thanks a lot
Thank
and
you.
Okay.
bye.
Bye-bye.
Bye.
Bye, everybody.